So hello, everyone, and I'm delighted to introduce today's speaker at the math seminar at the University of Prishtina. We have a great friend, someone who has contributed and is contributing enormously to promote mathematics, not just in Albania, not just in Kosovo, but in the Balkans and elsewhere, and a good friend of mine, and I'm really delighted to have you here with us, Tony. So it's Tony Shaska from both Oakland and Vlora, who will be speaking about machine learning in the moduli space of curves. So thank you again, Tony, for accepting our invitation, and we are very happy to have you with us.
Thank you. Thank you very much for inviting me. I mean, I've been to Prishtina about 10 years ago, I think now, or for something like that. I spent a summer there, and It was a good time. Anyway, so I thought about what to talk, and I chose a topic that it's a little bit more exciting. I could have chosen some of the traditional work I've done, but this is a little bit more exciting, but it will be mostly on things that I plan to do, that what I've done. So take that into account. I mean, so this is a joint work with Vlora, who is getting into this type of mathematics and machine learning and using machine learning in algebraic geometry and number theory and so on. So let me see if I have some way to make this a full screen. Anyway, okay, we're good. So look, there are actually some methods or some attempts to use machine learning and to use artificial intelligence in algebraic geometry. And if you just Google, and you'll see things like this, and for some of them I have actually a lot of interest. So there is this Calabi-Yau landscape from geometry to physics to machine learning that was maybe I think several years ago. And then there is so he has published several papers on this machine learning in physics and geometry and that kind of stuff. But if you think of it from the historical point of view, I mean, what is really machine learning? I mean, machine learning is creating some databases and trying to learn general and draw general conclusions based on whatever information they have. And so the roots of this actually go a little bit earlier. And I think the big databases in mathematics that we know about was in the 60s. There was this famous papers, actually two papers, on Birch, Swittington, and Dyer conjecture. And they have basically, I think, the first attempt to use some kind of a computer techniques to compile a database of elliptic curves and minimize them, get some kind of minimal equation and draw some conclusions on that. So I would think, from at least my point of view, that was really the very first paper that was actually doing this kind of mathematics to compile a large set of data and actually then try to draw some conclusions to that. And that conjecture, which is one of the most famous conjectures now in number theory, Birch-Swittington-Dyer conjecture, is based on that data that they have there on those two papers. But then, I mean, some of us who were like graduate students in the 90s or so, I mean, what are some of the big databases in mathematics that everybody knew about, or maybe everybody in algebra and number theory? Well, it was Cremona's big atlas of elliptic curves. I mean, back then, I mean, this was a big book with a lot of elliptic curves and classified on the conductor and so on. But even earlier, that was the atlas of finite groups. So these were books that were in a very special place in the math library that only a few people knew where to find them, because they were accessed very rarely. I mean, those who know group theory, I mean, they know that you have to know a deal of group theory to understand really, or to read these character tables and to understand the atlas. But I mean, there are databases in mathematics that have been around for 70, 80 years or so. So, so what's new now? Well, I mean, well, one thing is that machine learning now, it's the talk of the town. We say, I mean, it's very, very much in style. But I mean, and because of that, we have a lot more tools, computational tools, and a lot of packages and stuff. And machine learning has become kind of a science on its own. So it's not simply just some attempts to have some data and use your judgment to draw some conclusions. We have now very organized approaches of how to do that. And so that's why I think this is a topic that definitely will pick up in the next decade or so. So, okay, so what are some of the questions, basic questions about the moduli space that we could actually learn from this kind of approach? Those of you who are not experts in algebraic geometry, I mean, the moduli space of curves, universally known as MG, this script M, is, well, the space, loosely speaking, is an algebraic variety, is quasi-projective variety. It's a space such that every point there corresponds to an isomorphism class of a algebraic curve of genus G. Or if you take characteristic 0, I mean, think about, take everything over the complex numbers, a Riemann surface. Every point there corresponds to the isomorphism class of a genus G Riemann surface. So we know this has dimension 3G minus 3, and that is actually easy to show if we had a little bit of time. But a lot of questions, and by the way, so the famous work of Deligne and Mumford, they won the Fields Medal on this work, basically to show that this can be compactified and talk about stability and semi-stability and all that. I won't get into technical things in this talk, but there are some questions that are very natural here, as for any algebraic variety. I mean, what is really the singular locus here? So what are the singular points there? And by the way, if you pick a point there in MG, so you have picked some curve of genus G, or Riemann surface. What is the automorphism group of this? Or what can it be? What are the possibilities that the automorphism group of a genus G curve? Now, keep in mind, the automorphism group of a curve is invariant of coordinate changes. So the equation of the curve can change, but the automorphism group doesn't change. So being that invariant, that depends on this moduli point P. So it depends on the isomorphism class of curves. So simply stated, this says that two curves which are isomorphic have isomorphic groups, isomorphic automorphism groups. All right, and then the other thing is now, if you know the list of these automorphism groups, well, some of them will be actually subgroups of some other ones. And so is there some kind of an inclusion among these loci or some stratification that you can do of the moduli space based on the automorphism groups? Okay. For some of these things, we know the precise answers, or at least we know a lot. And for some other ones, we have no clue. So next one, for example, is something that it's very little is known. So if you give me a point P, then you take the Jacobian of that curve. Well, the Jacobian, again, does not depend on the coordinate change. So it is an invariant of the curve. And the Jacobian, normally, the Jacobian has endomorphism ring to be isomorphic to Z, to the integers. But for some cases, they might have a higher endomorphism ring. So these are what we call these Jacobians with complex multiplication. So if you have heard in the last few months, I mean, last summer, for example, the breaking of this Shaska. Shaska was super singular isogeny-based cryptography. And it was one of the big hopes of post-quantum cryptography. So got millions of dollars in funding and got a lot of attention, but it was broken. Anyway, super singular curve means a curve where the Jacobian or the endomorphism ring is larger than usual, okay? So just try to connect it with some of the terms or terminology that we hear nowadays everywhere. Okay, so I think it would be a very interesting problem, and I don't think anybody has any clue about this. How is the distribution of these points in the moduli space which have complex multiplication? Can we say anything about this distribution? I mean, what happens? Which points do have complex multiplication there? I don't think we know an exact answer to this, even for genus 2, which is the first case and the simplest case. So this is a famous conjecture of Oort, Francis Oort, and a lot of people have worked on, including Shimura, and a lot of people have worked on, so this is a big topic, on curves with complex multiplication. We call them CM curves, but technically the Jacobian has complex multiplication. Anyway, well, what else? I mean, if you give me a point P in MG, what does that mean? Can we describe that explicitly? Yeah, maybe for G2 or 3, maybe we can say something about it, but you know what that means. So we need some invariance of the curve such that uniquely they determine, you know, this isomorphism class of the curve. And I remember a good friend of mine who used to say, well, all our lives we are taught about these algebraic curves, and we are taught about their equations. I mean, in high school, we learned the equation of the ellipse is this, the circle is this. The equation is absolutely useless because the equation changes. And it is like a dress that you can, you know, every day you change the dress or you change the shirt or you change something. That's what the equation is. But it is not an invariant of the curve. So this point, the moduli point there, which is a fancy thing to say, well, some kind of invariance that we should be describing. Now for quadratics, for example, for conics, I mean, we have basic linear algebra. We can take this equation and diagonalize it and talk about eigenvalues and stuff, but that doesn't quite work exactly in higher degree equations. Anyway, there is a very interesting thing in this thing here now. If you say you know some kind of a description of that moduli point, okay, now let's just assume that is a rational number. So this invariance of the curve are rational numbers, okay, for simplicity. Does that mean that the curve is defined over the rationals? No. Okay, so that is, those of you who know, that is actually the saying, if that would be the case, that would be saying that the moduli space is a fine moduli space. But actually, we know that the moduli space is a coarse moduli space, so it is not a fine moduli space. So there are actually, invariants are given in terms of the coefficients of the curve. So if there is a curve that is defined over the rationals, invariance will be a rational numbers, but the other way is not true. But now, of course, I mean, one would ask, I mean, even for genus 2, that we can do these things explicitly and have algorithms and we know everything in detail. What is actually the distribution of these points in the moduli space where the field of moduli is a field of definition? What that means is that if you give me rational invariance, I can come up with a curve defined over the rationals. Now, there is a theorem that says that you can always do two quadratic extension. You can always, if you give me rational numbers, I can always find a curve as a quadratic defined over a quadratic extension of that. But for a lot of curves, I can get the field of moduli to be a field of definition. But nobody has any idea what is the distribution of such points in the moduli space. Okay, so that would be actually this next point here. Okay, and then there are a couple of things that I stumbled in this for the next two items. I stumbled on this, you know, when my former graduate student was writing her thesis in 2015, 2016, and then I continued this, and I'll tell you a nice thing that happened with this. So there are two types here of things that we call them reduction, or we want to do the best. Given a point in the moduli space, normally this is a projective space is there some way that I can get this invariance as small as possible? These invariants are actually up invariants of SL2. So they are not really invariants, these are SL2 invariants, but if you let a GL2 action, if you act with a GL2 matrix, they do change. So is there a way to actually get them as small as possible? Now, if you take them as a point in a projective space, of course, you can divide by the GCD, and that's easy. But you will see later on that this projective space is not very good. And so we want to look at the weighted projective space. And in that weighted projective space, we want to take this moduli point to have small coordinates. I mean, intuitively speaking, to have as small coordinates as possible. And then this point here now, let's just say you know how to actually recover the curve. Once you give the moduli point, you know how to recover the curve, or in other words, to actually build the equation of the curve. But is there a way that you can get the equation of the curve to be with minimal coefficients? So as small coefficients as possible, because, you know, I mean, normally if you pick an algorithm that it's out there, even for genus 2, I mean, you'll end up with, I'll show you examples, like coefficients that could be absolutely huge. So can we actually somehow get the best possible dress? The equation was the dress, right? The prom. We want to get the prom dress, right? I mean, a nice equation, minimal. Okay. And so I've been wondering about these two things and publishing little things on both of these two last questions. And I wrote a paper a few years ago on this reduction for superelliptic curves. So hyperelliptic, but generalized idea of hyperelliptic curves. For I called it reduction type A and reduction type B. And then later on, when I somehow stumbled, I looked at this paper of Birch, Swittington, and Dyer that I mentioned above. I was shocked to find out that they were doing exactly these two reductions. I call them, I don't know, the names were different, but they were doing exactly these two reductions when they were compiling this database of elliptic curves. Now, of course, that is very easy for elliptic curves. I mean, to do even reduction A, even reduction B. I mean, reduction B, you just have one invariant, which is the J invariant. Okay, so actually to get that minimal, when you look at it as a projective point, it's actually a very easy thing to do. But anyway, I was actually quite surprised and pleasantly surprised to understand at least that, okay, so it seems like I'm kind of on the right path here, not far from what one should be doing. Okay, so well, let's see a little bit what we can do out of these things. So there are two main methods in ML methods or machine learning. I will not spend a lot of time with this. I mean, these are things that you can, I got them from this IBM site, but you can Google things and figure out some of this information. So there are supervised learning and unsupervised learning. And then normally there's a third one, which is some kind of a combination of using supervised learning and unsupervised learning to kind of have a combination of the two, okay? So roughly speaking, a supervised learning is what? Well, you just enter the data and you tell the machine, basically, you tell the system what this data is and what it means, right? And unsupervised learning is when you actually have a bunch of data and you just let the system or the machine, let's say, figure it out in its own if there are patterns and so on. So we definitely will want to do supervised learning. I don't know, not because I like to have things under control, but I think we can use a lot of things that we already know about genus 2 and genus 3 curves and maybe even higher curves. And we can use a lot of things that we know, and then we can actually try to orient it or lean it on the right direction for higher genus things. And so, okay. So another thing that we do here, I mean, you are going to create this data set, right? There are some issues. First of all, how are you going to write these points? I mean, how do you describe these points? And by the way, any set is as good as a set, right? But if I have an ordering on this set, that is very nice. I mean, for elliptic curves, well, you have the J invariant. This is actually a rational number if you're talking about elliptic curves over the rationals. This is well ordered. We can, you know, we can talk about how to list this. In general, I mean, these are tuples of invariants. And so how do we do that? So to have some kind of an order and to have some kind of a counting method of these things. Okay, so for this, we will have to go into a little bit into the so-called weighted projective spaces and something I'm very proud about that was introduced a couple of years ago, 3-4 years ago, actually. This thing like weighted heights, okay, on these weighted spaces. It gives us a way to actually list things and talk about ordering points in the moduli space. Okay, so look, this is all talk, and theoretically, yes, we know these things, but what can we actually do explicitly? So the genus 2 curves, or genus 2, is the first example, not very descriptive or not very general. It's a very special case, but it is the example that we understand the best. Why is not very descriptive? Look, every genus 2 curve is hyperelliptic. So every genus 2 curve can be written as y squared is equal to a polynomial equation degree 5 or 6. That's not true in general for higher genus. And so this belongs to a very, it can teach us a lot about hyperelliptic locus. For every genus, you have a hyperelliptic locus, you have hyperelliptic curves. So it can teach us a lot for that case, but in general, it's not the overall case, okay? So for genus 3, for example, we have non-hyperelliptic curves as well. So remember how I said that the moduli space has dimension 3g minus 3? So 3g minus 3 here for genus 2 will be 3 times 2, 6 minus 3. So the dimension is 3, right? The dimension of the space of the hyperelliptic curves is 2g minus 1. So in this case, that will be 2 times 2 minus 1. So it's still 3. So only in this case, the whole space is equal to the hyperelliptic locus. Okay? So how do we describe these points? Now, Bolza, oh, I feel like I know him. I actually read his thesis when I was writing my own thesis. In 1887, actually, it was his inaugural thesis at University of Göttingen, PhD thesis. Quite amazed when I found it out. Talked about this invariance of binary sectics, and he defined them. So if you give me a curve, any genus 2 curve is written this way. And now the invariants of this are these J2 in terms of these coefficients A0 through A6. J2, J4, J6, and J10. Now, J10, I just was lazy and didn't want to write it because it's long. It's like a couple of pages. It is just the discriminant of this. So the discriminant of this, anybody from the 5th grade knows how to find the discriminant, right? Well, at least for the quadratic. But anyway, it's just the resultant of the polynomial and its derivative. So that's easy, but it's long. And it has degree 6, I mean degree 10. Notice the other one, I'm writing this degree 2 because it's a homogeneous of degree 2 polynomial in the coefficients. And so J4 and J6 and so on, okay? So these things determine, somehow, they determine the isomorphism class of the curve, okay? And that's how they determine them. So keep in mind, these are SL2 invariants. What does that mean? If you just replace here X and Y with some linear expressions in X and Y, the corresponding matrix, it's not an SL2 matrix, it doesn't have determinant 1. And so, of course, these things will change, these invariants. How will they change? Here is how they will change. So if 2 curves are isomorphic, I mean, they are isomorphic if and only if their tuples relate this way. So there is, did I do something? Sorry.
I think so, yeah, but no, you're back.
Okay, sorry. So they are isomorphic if and only if there is a non-zero constant, such that there is this relation between them. So the tuple of the, let's say, C prime of the new curve has this relations, lambda squared. Remember, that's the same as the weight of the invariant, right? Lambda to the fourth, lambda to the sixth, and lambda to the 10th. So this is the relation between invariants of two isomorphic curves. And by the way, just by looking at this, we say, okay, this reminds me of some kind of definition of the weighted projective spaces. And I'll do that a little bit later in more detail, okay? So weighted projective spaces are basically, you've taken a affine space, and then each coordinate of that, it has different weights, and you define this kind of similarity or this kind of equivalence relation basically by this line here. I'll come back to that. Anyway, so it seems like, I mean, these two tuples like this, I'm sorry about this, I don't know what is happening, correspond to the same point in the weighted projective space, okay? And so what that means is that isomorphism classes of genus 2 curve correspond to points in this weighted projective space WP with weights 2, 4, 6, and 10, defined over the field K. Okay, there is a way to actually embed the weighted projective space into a projective space, so-called the Veronese map, okay? So what you can do, the trick is, well, you lift each one of them to exponents such that each one of them has the same combined weight. So notice how I'm doing it. J2 goes to the degree 30. So that will be a polynomial of degree 60, right? Because 2 times 30 to the 30 power. And so for each coordinate, 4 to the 15, 6 to the 10, and so on. So you can look at this now as a point in the projective space. And you can even say, well, something better. J10, I know it's the discriminant. That cannot be 0. Because if you let the discriminant on the right side here be 0, then by this Plucker formula, as the genus goes down, it has singular points. And so the discriminant cannot be 0. J10 cannot be 0. And so I can divide by that, and I can take an affine version of this, right? And so sometimes you will see in the classical literature, two genus 2 curves are isomorphic if and only if this, we call this absolute invariance, little I1, I2, I3, these things are the same. Now this, you think of this 3 as the J invariant version for genus 2. So the J invariant for elliptic curves, which I'm sure you've seen or heard, two elliptic curves over the algebraic closure, right, are isomorphic if and only if they have the J invariant. And the J invariant is just a number given in terms of the coefficients. It's some ratio of two things, right? And that's exactly what these things are. There is something very stupid about this. And what is that? Yeah, it's nice to claim this and to explain, and this looks wonderful. But if you see the coefficients, I mean, of these things, and now taking this J10, and by the way, I said J10 is much bigger than the previous ones, and raise that to, whatever, to the 6th power, this becomes a monster. I mean, so these are, from the computational point of view, something you just don't want to deal with. Okay, so the smart thing to do is actually deal with this. Why take this and raise them to coefficients and so on? Just deal with these invariants as you have them. And in order to do that, that means I have to deal with this weighted projective space. So that is our preferred way of actually storing or creating points in this weighted projective space, okay? And so I will not say anything else about this, but theoretically speaking, this is possible now for any genus, but I mean, these things are not totally explicitly well known. I mean, in genus 3, we know them, but even in genus 4, you start having problems because not everything is hyperelliptic. And so, what does it look and what is it? Well, there is a theory of GIT that says theoretically it's okay, but explicitly it's not. I want to show you this picture, and this is an honest to God picture, right? I mean, this is not made up stuff. Now, in genus 2, the automorphism group of the curve can be of order 2. Every hyperelliptic has hyperelliptic involution, so of order 2, but could also be V4, the Klein 4 group, which is this top picture here, or it could be two subcases of that one, so a dihedral group of order 8 or a dihedral group of order 6. And these are one-dimensional thing, and this is a two-dimensional thing. These are pictures actually written of this surface using this invariance here, okay? So I actually let it run all night in Mathematica because these invariants are so big, so you have to shrink it a lot and then to get some kind of a thing. But you can see there is actually a singular locus here, and there is also some kind of an edge there. So this singular locus of this surface are exactly these two loci down here of curves that have a larger automorphism group, namely curves with automorphism group of order 8 and 12. And these are the only curves here that have extra automorphisms. There is also one point, a curve of automorphism group of order cyclic of order 10, but that is just one curve only. Okay, so that's kind of what we want to do. We want to understand in general what that happens. So I created this genus 2 database long time ago, actually. I think it was around 2015 when Bershai was writing her thesis. And so these are some of the things that when we were creating it, we were kind of wondering and changing our mind what needs to be stored and what not, okay? And so these are some of the functions of that package in Maple. We are converting it now to Sage or something else to make it accessible to people. But you notice, you know, invariants, now Igusa, Klebsch, and these absolute invariants are invariants that have been used all over the place. So this is mostly to convert from one version of the other. Different people use different things. But, you know, rational model. So that means you give me any curve, I can find a curve isomorphic to that, defined over a minimal field of definition. Okay, so minimal field of definition, it tells you what that minimal field of definition is. Rational form means you give me some invariance, some rational invariance, and I can find the equation of the curve defined over the rationals when that is possible, because that's not possible all the time. Anyway, so I won't go into these other things here. So there are plenty of things in this genus 2 case, but this is something that we know, at least I know in detail, even though a lot of these things is not public and it's not. Even the other day, somebody was asking me for this genus 2 package that I have it for 20 years now. So people who deal with this kind of stuff, they know who to ask. But unfortunately, I wish this would become public and everybody could get this. Anyway, can we generalize these things? Can we do this for any higher genus? And the answer somewhat is, yeah, there are ways. So a curve, there are three ways to think of an algebraic curve. Well, geometrically, that's the locus of 0 points of some polynomial. But another way to think about it, it is a cover to P1, okay? And a third way, it is algebraic, a field extension of a genus 0 field, okay, of a function field. So function field extensions and stuff. It depends on whether you are a topologist or a field theorist, you know, or a geometer. But anyway, this approach with the covers, it's very nice because it gives us a way to actually get this data for the automorphism groups. So I will skip some of this because this is topology that I love it very much, but it will take me a little bit of time, okay? But so there is the fundamental group. These are the branch points Q1 through QR, the fundamental group acting on the fiber. And that's how you define the monodromy group. And that defines what we call it the signature of the curve, of the covering, or the branch cycles. So once you fix the monodromy group and the signature of this covering, so the branch cycles, then this is called a Hurwitz space. They are actually families of such covers form what we call it, and I am not being totally technically correct here. They form these quasi-projective varieties. Okay, so they are algebraic varieties. And by the way, just using group theory, I can determine the dimension and of these varieties of each component. I can determine if they are actually irreducible or not, the number of component, the genus of each component when they are curves, and so on. Okay, so this is done via this Hurwitz, this braid action. Okay, and so this is all implemented in GAP, and one can actually do it. So the number of this, so under the braid action, you have a bunch of orbits. The number of orbits corresponds to the number of components. So if there is one orbit, there is one irreducible component. So they are connected, okay? Irreducible. So there is some connection, well, not some, there's a big connection of this to the inverse Galois problem, but I will not really go there. What I would want to say is this thing. If you give me that cover of the curve to P1 and you fix the monodromy group and you fix the signature of that cover, then I can actually define the following embedding from that Hurwitz space. Hurwitz space now is the moduli space of those covers, right? To MG, to the moduli space of curves now, by taking that curve, taking this curve X and sending it to the isomorphism class. So all of this, it's kind of preserved. So isomorphism classes of curves correspond to isomorphism classes of coverings. I skipped that part here and so on. So things work fine. So you have these Hurwitz spaces now embedded into the moduli space of curves. So this gives us a way to actually look at covers and determine exactly, well, what is the dimension or what is the inclusion of these things as subspaces of the whole of the moduli space. All right. One thing I wanted to get your attention to, if you look at all the 19th century mathematics, starting from, Legendre and elliptic integrals and hyperelliptic integrals and Jacobi and Abel and later Riemann, and going all the way to 60s and 70s with books of Mumford, all the examples come from what? Well, hyperelliptic curves. If you look at the book of Mumford, the Stada lectures and curves and their Jacobians and stuff, all the time it comes like this. Why? Because they are easier to understand and because we have no idea in general what is happening. But what is so special about hyperelliptic curve? Well, what you have a degree 2 covering from that curve. So this covering now from X to P1 is a degree 2. Well, every degree 2 covering gives you a degree 2 extension. So from K now to Kx, this is the function field, right? Degree 2 extensions are always Galois. So you actually have an automorphism fixing that extension. This is exactly, or another way to say, a complicated way to define the hyperelliptic involution, which is basically permuting, x and minus x. That's a typo here, sorry about this. So this should be xy goes to x minus y, sorry about that. Okay, so this hyperelliptic involution is central. You can mod out, take the quotient group, and you create the so-called G bar, or the reduced automorphism group, which is G mod out that hyperelliptic involution. Now, this G bar is a automorphism of a genus 0 field, or an automorphism of P1. P1, the function field of P1, the Riemann sphere, is a genus 0 thing, right? Well, what are and it is finite. We know this, it's finite. So what are the finite subgroup of automorphism group of P1. By the way, the automorphism group of P1 is PGL2, right? So what are the finite subgroups of that? Well, there's a classical theorem from complex analysis. It's one of these 5 types up to isomorphism, right? So it's a cyclic one. It could be a cyclic group, a dihedral group, and A4, S4, and A5. So the whole group here, the whole group G, is a degree 2 central extension of one of these. And that's how you figure out the groups for hyperelliptic case. Now, what about the superelliptic case? We'll replace this hyperelliptic case here, I mean this involution, by a degree n normal cyclic subgroup of order n. And so everything else stays the same. So they will have y to the n is equal to f of x, this type of equation. So this has been kind of I made a living with this for the last 15 years, academically speaking, okay? That's what I have been focused on. Why am I mentioning this? Because curves like this, which I've called them superelliptic, are about 80 to 85% of all the cases in the moduli space. So if you list all the groups, automorphism groups, they're about 80 to 85% of the cases. Okay, so I will have to skip some of this, but look at this now. This is genus 3. This is genus 3 on the left, this picture. So the blue case is the hyperelliptic case. The red one, non-hyperelliptic. Okay, so notice now, and you get on the right, you get the dimension. So how should we understand this? Look at this C2 here on the very top. On the left here, the dimension of that locus is 5. We know that 2 times 3 minus 1, so it's 5. But there is also genus 3 curves which have automorphism group C2, but are not hyperelliptic. And that is this C2 here, that has dimension 4. Now, what are these other things? V4, of course, this V4 on the blue here is the Klein 4 group. And the Klein 4 group, of course, has the C2 inside, right? So that is a smaller dimension because that is a sublocus of the big hyperelliptic locus, right? So that's what I mean inclusion among the loci. So if you get the big locus here, there's a 5-dimensional subspace. A sublocus of that is the V4, and a sublocus of that is the C14 and all these other cases. And the same thing happens now for non-hyperelliptic cases. Okay. Now look at genus 4, this picture on the right. And by the way, we have known this since I think 2001 or 2002. So for some reason, which I don't remember or recall, I have changed the colors. So the red ones here are the hyperelliptic ones. The blue ones are the superelliptic ones, and the yellow ones are the ones that are not superelliptic or hyperelliptic. By the way, technically speaking, a hyperelliptic one is superelliptic, right? And you see, I mean, I think from 41 cases, I think only 13, if you count them, only 13 are not superelliptic. So the majority, it is superelliptic. Yeah, here it is. And by the way, for all the superelliptic curves, which are these cases now here on this table, we know precisely the equation, we know the automorphism group, we know pretty much everything there is to know about them, including this inclusion and stuff. Okay, so in general, we can do this, maybe, and I think I should say something like this. Diagrams like this, I can construct, and this has not been published anywhere, and it takes a little bit of time to make it publishable, all the way to genus 48. I can construct diagrams like this, inclusion among this. And the reason that I stopped at 48 is because when we were doing this, the gap library of small groups went up to groups of order 1000, and up to 48 we only found like 3 or 4, or these are based on this Breuer's for database for signatures of covers, And so there are only 2 or 3 cases when the group has order bigger than 1,000. And then if you continue, I mean, you get more of these cases. And we had actually a hard time to justify this. For example, if you look at the 3rd column in the table, when I say 18,2, that is the gap identity of that group. That means it's order 18 and is the 2nd one on the list. Now, which one it is? I'm not sure, but you can go there in gap and say, display the group with gap identity 18,2, it'll tell you. Most likely 18,1 is the cyclic one, 18,2 is probably some cross product, I mean, yeah, direct product of Z3 or whatever, Z2 cross Z9 or something. You have to see, okay? But we stopped mostly for technical reasons, not because the theory becomes harder or anything like that. Okay, I will skip this weighted projective spaces. I mean, it's actually a nice introduction of this. This is the equivalence relation that I was actually talking about. So a point in the weighted projective space is actually the equivalence class of this relation. Okay, so these are known, but not that known to my surprise. Okay, so there is, again, the Veronese embedding in general now for these spaces, and there is actually, let me skip some of this. I'll show you, hopefully, so we have a height for this and all that. I will show you, hopefully, maybe not. I thought I had some example, maybe not. So some example where building this rational model of genus 2 curves where things, I mean, if you just use algorithm of Mestre and stuff without doing any reduction, I mean, these coefficients are absolutely ridiculous. And when we do our reduction, they get a little bit smaller. So let me skip through some of that and try to conclude. So this is a nice theorem about this. Remember the CM curves? So I had a paper with Andrew Obus, which was published in this Mathematics of Computation about 2 years ago. And what it did, it generalized a paper of Richard Pink at ETH in Zurich. So they actually wrote a paper based on a previous paper of mine on determining which hyperelliptic curves with extra automorphisms have complex multiplication or not. And we did this now for all supraelliptic curves. And this is basically the theorem which tells you all the supraelliptic curves with extra automorphisms, yes or no, which one it has and which one it's not. And the last column it refers in that paper, which is long and technical, where the result comes from. So this is interesting, but I won't get there much. The whole point is this: can we actually make this work? And maybe not. I tell you this, and I'm not making this up, okay? Last week, my little boy, which plays with he's got his own set of tools, saw me. I finally decided to do some work around the house and had a hammer trying to get something out of the dishwasher there. I mean, try to get the dishwasher out. And surprisingly, I mean, honestly, surprisingly, he goes to his room where he keeps all the junk and all the toys and grabs this little hammer there and comes next to me and tries to actually help me out. And I'm thinking, well, what is it? Is it the shape? Or it is actually because he has a lot of toys there and some of them might actually resemble this more than this little hammer. Was it the shape, or is it that somehow in his little mind he has figured out the process or what this tool is supposed to do? But it actually shocked me, and he's like 1 year old. So it absolutely shocked me to realize that he did make that connection. And yes, they look kind of in the shape, maybe similar, maybe not, I'm not sure, but so can we somehow recognize certain patterns? And the main thing here is, well, how to define these patterns. And so that is something that it's still kind of work in progress, but I think the genus 2 case, it's a great learning example. The genus 3 case should be even better. because it is the first case where you have the non-hyperelliptic curves, okay? And so this is a list of things that I would like to do during the summer. And Genus 2, it's pretty much complete. There are questions there in arithmetic statistics and arithmetic of moduli curves, but that is pretty much well understood. Genus 3 case, well, something that we are working on, and higher genus, especially figuring out how to describe the point in the moduli space of figuring out invariance. This is something that I think it would be a great contribution, and hopefully we can get a little dent on that in the next few months. I got help. I'm not doing this alone. So now I have some people who know how to do this kind of stuff. I mean, I understand some of the mathematics here, but I'm no expert in implementing these things in Python and things like that, and actually trying to get it done. So I have some help now, and hopefully things will move on a little bit faster than in the past. And I will stop here. Thank you.
Thank you very much, Tony. Thank you for this wonderful talk. And I guess you have some help from not just your students, but also your son. So there's already a question that has been asked in the conversation. So this is Hamdi, who says, can I ask what kind of results, I'm sorry, I'm trying to read it, about MG you would expect to get from the case of superelliptic loci? So this is what he's, Hamdi?
Yeah.
Yeah.
Yeah, I mean, so for the superelliptic cases, we absolutely know everything about every genus. So you give me the genus, and you can dig it out from my papers, or I can tell you where to look, but you can actually get a table of automorphism groups, and for each family, you can get the dimension of that locus and the parametric equation of that family. So they look like y cubed is equal to blah, 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 or y to the fifth, and so on. Because we look at the structure of the automorphism group, we know exactly which one are the cyclic subgroups. And so I can give you precise tables for those cases. And those tables were part of one of my PhD students' thesis 15 years ago. That's what they were used by Richard Pink and his PhD student in ETH. That's why he studied, I mean, these curves with complex multiplications, because he looked at these tables and said, well, can I actually say something about each case? But yeah, to give you a short answer, we know everything if you fix the genus about the superelliptic case. Here is the problem. The curve, I mean, the moduli space is much bigger. So even though we know a lot of things for the superelliptic case, well, these things still have measure zero, right? I mean, the curve, the space is much bigger. And for that one, it's a little bit more difficult.
Okay. So does anyone else have a question? Thank you. I had a brief question. You mentioned the weighted projective spaces, and so I've come across those when studying pluric varieties.
Mm-hmm.
And your comment about them, I was trying to understand.
Well, my comment is this. I mean, that is the natural way to look at the moduli space of curves.
Mm-hmm.
And that is absolutely the easiest way and the natural way. And by the way, the projective space is a special case of the weighted projective space when all the weights are one. So the right way to look at it, but the weights are not one in general. I mean, even for genus 2, the weights are not one. So because we never understood them, we make them one by getting into a much larger projective space via this Veronese map. So why do you do that? Because that has cost, right? I mean, you go to a much larger projective space, well, you're losing something. So it's absolutely much, much nicer to do things in the weighted projective space, in the original one. And now the question there is, well, what can you do? Can you do arithmetic in those spaces? And so I was actually shocked that there are some publications on this, but not as much as I expected. So one of the things that we came up with in this paper a few years ago, with this idea of this weighted GCD. So what is the weighted GCD? In a projective space, you can take the GCD of all the coordinates and throw it out because, you know, it's up to multiplication by a constant. Well, now that doesn't work here. But when you pull out the GCD, that has to be such that in the first coordinate, you pull out lambda square, in the second lambda to the fourth for our case. So in every coordinate, you have to pull out a constant to that weight. And once you pull them out, you get like the smallest, the minimal representation of this point in the weighted moduli space. And that leads to some very interesting cases. I mean, in the tropical toric varieties, but also things like this. I mean, you can find the GCD of two numbers in a polynomial time algorithm using the division algorithm, right? Sorry, I mean, I have two screens, so I keep looking at the big screen, and now I realize I'm not looking at the camera.
No worries.
Look, I mean, GCD of two numbers, you can get it by using the Euclidean algorithm, right? But can you do this for the weighted GCD? Because the way I have defined the weighted GCD is that such each coordinate is assumed to be factored. So can you use this without actually factoring? Can you find this? Which leads to maybe, is there some kind of a division algorithm, but now for these weighted projective spaces, so for weighted spaces? So a weighted division algorithm? I don't know. I mean, but they are absolutely interesting. And I think I definitely will be very interested to talk about this if you have some interest on this.
Great. All right. Thank you. Thank you, Tony. Does anyone else have a question? One last question, maybe?
Can I just ask another question? Yes. If that's okay.
Please.
So these super elliptic curves, I know that for like elliptic curves, and you've got like these notions of elliptic curves as in the combinatorial or like the tropical version of them. So I was just wondering, is there like a tropical version for super elliptic curves, or is there a notion like that that could be in handy somehow in tropical toric geometry?
Honestly, I think I have seen some papers where people kind of have wondered a little bit on that, especially on hyperelliptic curves. I mean, there are a couple of people in Oxford and their students are doing something on genus 2, for example, and things like that. I mean, theoretically speaking, yes, there are. Explicitly, what has been done, I'm not aware of much that has been done, you know, in general, but that is actually a great point and a great question. And I have thought about it, but I don't know enough myself to invest a lot of time in that direction. So unless I find somebody who knows more about this, I'm not willing to take it on my own. But yeah, that's a great point.
Thank you, Hamdi. I think nobody's, yes. So I think this is the moment when we thank you, Tony, very, very much. And we really look forward to hosting you in, you know, in real flesh here in Prishtina.
Okay, well, thank you. Thank you very much. And let me congratulate you for this wonderful initiative. And I hope we'll see each other more and more. I'm on sabbatical next year, so who knows? I might actually drive all the way there at some point.
Yes, you're very welcome. Thank you so much, Tony. And thank you, everyone else. And see you in a few weeks for our next seminar talk. So thank you. Bye-bye.
Bye. Bye. Ravs,